Welcome everyone. We're ready to continue our exploration of the IP layer with the perhaps most embarrassing part, which is how IPv6 is avoiding to use broadcasts, which is something that has been visible last week when we have seen how IPv6 uses address resolution, performs address resolution. I recall that address resolution is the problem where a host or a router knows the IP address of something, of a destination, and needs to know what is the MAC address that goes with it. And the IP way is very simple. You simply send a question to all hosts who are likely to have this address. In IPv4, we'll see this is done by broadcast. In IPv6, this is done by creating what is called a solicited node multicast address, which is explained here. It's a multicast address, and it's made out of the last 24 bits of the target IP address. So if the target IP address is this one, 24 bits means how many hexadecimal digits? 6. So we should take the last 6 digits of the address, except now there's a trick. It's not the last 6 in this notation, but in the uncompressed notation. So you need to uncompress first to take the last 6 digits. In the uncompressed notation, here they are. So you put them to the prefix that is reserved for this type of addresses. And if you compress again, that gives this. So this is the solicited node multicast address that corresponds to this target address. And the rules of IPv6 is if you are a machine that has an interface that has this address, you should receive all the multicasts that correspond to that one. Right. IPv4 does the same thing using broadcast. So with IPv4, the problem is exactly the same. The solution is also the same. The naming is different. We call that Address Resolution Protocol, ARP. And many people, even with IPv6, will continue to call it ARP because it's such a well-known name. The difference is that ARP packets are broadcast to all nodes into the LAN. So if a host wants to know what is the MAC address that corresponds to an IPv4 address, you will do the same as we've seen, except it's truly broadcast, which means everybody will receive it. IPv6 was trying to avoid broadcast by having the multicast, but now managing multicast is adding some complexity, so it's not clear whether it's a good idea. When you move to IPv6, you have to manage all those multicast groups, which sometimes is perceived as an added complexity. Question? Why did they want to avoid broadcast? That's a good question. Broadcasts, in principle, might be a problem. We will see that if on the LAN, for some reason, there's one link that's very long, for example, and costs a lot, you don't want to have a broadcast whenever somebody there is asking what is happening here. So the broadcast may cost a lot. Worse, there were in the past instances of bugs in systems where when a system received a broadcast message, it would respond to it. Like if you receive a ping request, normally you respond to it. If the ping request is sent to the broadcast address, and if the system responds to it, then you generate what is called an avalanche, a cascade of broadcasts that kills the network instantly. That happened. It did happen. So due to bugs, it was not even malicious, it was simple bugs. So there is a track record for people who have managed networks of having problems because of broadcasts. An industrial network today, an industry-grade network, will try to filter all packets. So in addition to everything we see, usually there are systems that are observing all the traffic and ask the question, is this packet legitimate here? Right. Broadcast, it's very hard to see whether they're legitimate because you need to understand why the broadcast was sent. So if you kill all broadcasts with IPv4, some things won't work. With IPv6, it's easier to filter because you know this packet, for example, is an NDP packet that is asking for an address of that group. But the way I've allocated addresses, there's no reason that anybody is on the left, so I will kill this packet here. So it's easier to filter packets if you have multicast addresses. It's easier to do complicated things, but it's more difficult to do simple things. This is an ARP packet or an NDP packet in IPv6. In IPv6, we see that we have Ethernet, IP header, and then inside the IP packet, there is an ICMP, which is the control message and error protocol for all of IP layer, which is sort of makes sense. With IPv4, there is an anomaly that the ARP packet is not an IP packet. The ARP packet is a protocol type called ARP. So inside the Ethernet packet, there is something that says this is an ARP packet. And inside the ARP packet, there is something that says the protocol that I'm trying to analyze is IP. The reason this was done is that when this was invented at the end of the 70s, IP was not the only protocol that was trying to do internetworking. There was IP. There were also other protocols like DECnet that were doing that. There were also OSI protocols. So there were the vision was that there might be multiple things. IP might not be the one that survives. So ARP was done as a generic mechanism for any network layer protocol to solve the problem. Of course, this is not what has happened. IPv4 became the dominant protocol. And when there was another protocol, which is IPv6, that would have been a good opportunity to reuse the same. But as we see, we did not reuse ARP, but we use ICMP to do this. So those are anecdotal little complexities that if we would redesign the system entirely from scratch today, we would not do it this way. But this is how it is. Time for a little quiz. What will M1 do in this case here? And now you see that the majority is saying B, which is right. So there was a little trick here. Of course, when M1 wants to speak to M3, because there is a router in between, M1 will send a packet to whom? At the MAC layer, to the router interface. So M1 wants to find the MAC address of the router, which is here, P.1 here. So answer B is the correct answer.
Wouldn't it be sent when it connects to the router, not when it's connected?
It doesn't connect to the router. M1 knows that the destination address is not in the same LAN by analyzing the destination prefix and its network mask. M1 must also know the address of its default router. So M1 knows, that's the IP algorithm, anything that I am sending that is not in this LAN, I must send to this guy, to this address, P.1. So M1 sends the packet using the LAN to P.1. Of course, the destination IP address is Q.1. But the MAC address that we will see in the packet is M9. Right. So if you do a Wireshark of the traffic from M1 to M3, here you will not see the MAC address of M3, which makes sense because a MAC address is used only inside the local area network. Remember, IP truly means internet. It's a collection of local area networks that are interconnected by the IP layer. This is how things are. Whether you like it or not, you can argue, why do we do that? But this is how things are. Somebody asked last week, how about the security of all that stuff? And the first answer is, well, in fact, there is a security problem with ARP. If a bad guy is faster than the good guy, the bad guy could capture all the traffic. Right? So this can happen. This can happen in particular if you're in an open environment, like a hotspot somewhere in the city. It is quite possible that the traffic goes to someone else, to a packet sniffer. So if you're in a hotspot, make sure all traffic you send is encrypted, or the hotspot MAC layer, as we will see, is protected by mechanisms that we will discuss in a second here. What are the mechanisms to avoid that? I mean, first, very often the mechanisms are not very strong, so there is always this risk. In enterprise networks, most of the time, so on Ethernet network, on cable networks, The Ethernet switches will do much more than just switching Ethernet packet. They will also try to do packet filtering and observe all the things that could be security problems. So one thing they will do typically, not necessarily, but very often will do, is what is called DHCP snooping. So what is DHCP? DHCP is a method that we will see in a second by which a host gets its IP address when it boots, or when you connect for the first time to a network. When you come in the morning to EPFL, your smartphone uses DHCP to get an IP address from the wireless network of EPFL. Now the device, if the device that speaks to you, the base station or the Ethernet switch, can also observe that, or very often the DHCP function goes through this device, it knows also which MAC address was given to you. So this device can know exactly which address is given to you. So if it's very smart, what it can do is answer on your behalf for any MAC, for any ARP question. If somebody is asking, what is your MAC address? Since the IP address was allocated to you by a device that knows what was allocated to you, and this device, if it is on the path of all the ARP packets, requests, it will answer for you. So this is what is called sometimes DHCP snooping. In what you can do if you don't do that function exactly, you can do what is called at least inspection. So by observing all the ARP packets and looking whether it makes sense for you that the reply comes from this port. For example, if you have a bogus guy that is responding with an ARP reply, and you see what is the MAC source address of this guy, and you know that this is not on the port on which this guy's the legitimate user is, then you can filter out this thing here. So it's typically deployed in enterprise networks, rarely elsewhere. There is another technique called secure NDP, which is more sophisticated and works only for IPv6, which uses cryptography. It uses asymmetric cryptography. It assumes that every host, and this is something that may come in a remote future, every host has what is called a public-private key pair. What is a public key and a private key? Well, keys are used for encryption. If you want to encrypt a message, make it secret, you use a key. And if you use symmetric encryption, you use the same key for encrypting and for decrypting, which sort of makes sense. There is a magical thing called asymmetric cryptography, where it's possible to have two keys, one that you use for encrypting and the other that you use for decrypting. And the two keys are completely unrelated, so that you can make one key public. And anybody who knows this public key has no mechanisms to find what is the private key. So they appear to be random and have no correlation to each other. So there are protocols called RSA and DSA to do that kind of things. They're based on number theory or elliptic curves here. So assume every host has a public key. Typically, this is true for any web server. If you run a web service somewhere, you must associate it with a public key, typically. So every host, assuming, has a public key here. The other ingredient is that the EUI is the host part of the address when we use IPv6, and this is typically 64 bits, half of the address, which corresponds to the host part. With this mechanism, we can derive it from the public key here. So we hash the public key and some other things, and we obtain the host address. Hashing means we take a function, which is also a one-way function, that translates the public key, which is typically much larger than 64 bits, and you translate it into, so you number crunch it, and you obtain a sequence of 64 bits. And also, like for cryptography, it is practically impossible, knowing the hash, to know what was the public key, other than by trying and doing brute force here. So the host part of B is derived from its public key. Now, when A sends an ARP message or a neighbor discovery message, then the response to A, which is the MAC address here, will be signed by B using its private key. What does it mean, signing? Well, the response is the MAC address of B, for example. Then what B can do is encrypt the MAC address with its private key. Typically, it will encrypt the MAC, a text that is made of the MAC address plus some other elements. But think of it as simply encrypting the MAC address here. Now, when A receives the reply, it cannot know what the answer is, but it can verify whether the answer it receives is legitimate. By doing what? By decrypting the signature using the public key, because the public key is public, so it's known to A. So A will decrypt the signature, and it can, if the decryption works, so there is a verification code in this. It's similar to what you do when you download some software somewhere and you have a signature that you can verify whether it's correct here. So A knows that it is certainly, or with overwhelming probability, it was signed by a device that knows the private key of B. So this is what A will know for sure. Now, since the address of B is derived from the public key, also with very large probability, it means that the address that I have received, the question that I've asked must be exactly for this address here. The hash function is public, so A can verify that the hash of the public key corresponds to the address here. So in principle, this should solve the issue. It requires IPv6, which is not widespread everywhere. There is a subtle problem with solutions like this one, is when you use cryptographic function, what is the problem? Not all receivers can decrypt. That's correct, but here we assume if you want to connect to this network, you have to have this software installed. Yes?
Every machine must have a pair of keys.
Every machine must have a pair of keys, but here this is solved by public key and private keys. So yes, you would need to have a public key for your device, but that's one of the requirements you have to connect to such a strongly secured network. There are mechanisms for obtaining public keys, public-private key pairs. Well, one of the major problems with cryptography is that there is no formal proof that cryptography is secure. It works as long as nobody, people like Serge Vaudnay or Ariane Lenstra at EPFL, has broken it. So cryptography works as long as it works. And periodically, something that was very secure is no longer secure. For example, RSA is considered unsecured if you have key lengths that are less than 2,000 bits, whereas 10, 20 years ago, RSA with key length of 500 bits were considered perfectly secure. Perhaps in the future, somebody will crack RSA and find a way to systematically compute the private keys from the public key, in which case you have to get rid of RSA. So I'm not saying this should happen, but this is how things are in cryptography. So once in a while, something that was considered secure, we find a flaw in it, which may be a flaw in implementation, in which case you need to change the software, or worse than that, it's a mathematical problem. There is a way with something that we believed was one way. In fact, there is a clever way to still recover some of the information. And if that happens, what do? You have to update your software. This is why you should constantly update your operating system. This is why every week Microsoft sends an update, and if you do the updates of iOS or Apple software, it always says somewhere the fantastic things that the update does, but the major motivation for the update is security improvements, which means somebody has found bugs in a number of cryptographic functions or other security protocols, and we're fixing them. So if you do that, then you start that game. That means your MAC layer software will need to be patched very frequently. So this will need to be done, and many people don't like that for the MAC layer software. For application software, it's no big deal. Many applications, they check the software whenever you use it. But for MAC layer software, it's a bit more complicated. You need to change operating system code. So this is a bit more tricky. In principle, it should be done, but today it's not very widespread. We have mentioned through this discussion a number of things that must be present in host configuration. Here is a quasi-exhaustive list. A host needs to work with IP those 4 things. The IP address of this interface for every interface, the mask, the IP address of a default router for this interface, and also probably the IP address of a DNS server if you want to use DNS, which probably you want to do, as we can discover in the lab here. Compared to Mac, we see that for running the Mac layer, we don't need any configuration. Here, with IP, we need some. You can do it manually, and we learn in the lab how to do that, but most of the time you don't do it manually, otherwise you would not have used the network of EPFL, for example. This is done by protocols that are typically called DHCP, Dynamic Host Configuration Protocol. For IPv4, it's very simple, and as usual, for IPv6, there are zillions of options, and we'll go through very quickly to give the flavor of some of them. Here is how DHCP works with IPv4. Assume you connect to some network based wireless or wired with your machine here. For example, that's at home when you connect to your ADSL modem. So you don't have an IP address, so you will communicate to somebody who can give you the IP address. With IPv4, this is done by using special tricks where we send. So first, we assume that in your local area network, there must be a DHCP function. In the simplest case, it is a DHCP server. A server means a piece of code that is waiting for DHCP requests and is able to respond to them. It is, for example, your ADSL modem that has rules for saying which range of addresses can be given to whom. And the rules are typically very simple. They just give the min and max addresses. And then the rules of the game are usually we give an IP address, it's a bit like in the NATs, on the fly by taking the next available address while making sure that 2 hosts that have the same MAC address, that have different MAC addresses, don't get the same IP address. So 2 different hosts should not get the same IP address. So this is typically done by using a message that is explained here. You send using UDP to the ports that are reserved for DHCP, and then the destination address is the broadcast address, which is used in IPv4 and is, of course, link local. This broadcast address will never go beyond the local area network. And the source IP address, well, we find an instance of the absence of address. Since you don't know what is your address, you send 0. Right. In this packet, there is also information like perhaps specific configuration information, but through this packet, the function that is here will receive in particular your source MAC address. Well, if the server is sitting here, it will find an available IP address, write in its table the MAC address that corresponds to it, and will respond to you by sending a response that will be sent to your MAC address and to the destination address, which is either broadcast or 0. Very often, however, you don't want to have a server on every local area network. We don't do that at EPFL, for example. So you have in enterprises, you have one big DHCP server that contains all the rules for configuration of IP addresses, who should get which address, typically depending on where you connect at EPFL. And now there is a chicken and egg problem. This client cannot talk to the server because the server is not on the same LAN. And in order to talk to somebody who's not on the same LAN, I need an IP address here. So this is solved by having an intermediate system of DHCP, which is called a DHCP relay. So we can think of it as an intermediate system of the application layer. You can view DHCP as an application that simply relays the messages. So this function, DHCP relay, is typically implemented in Ethernet switches and in ADSL modems. So it will receive the request, but instead of replying with the request, it will send the information further away to the DHCP server with information like on which LAN was this request coming. So by identifying the IP address of the relay here, it's typically done in a router or an Ethernet switch or some other device here. So it knows its LAN and the MAC address of the source of this message. So the DHCP server will have this information, will say, oh, there is a host that's trying to get an address. It is sitting on this LAN. It is on the BC building, 4th floor, for example. And here is its MAC address. I will give an address, 128, 178, 156, dot something, because those are the addresses that in my big table here, I have to allocate to the things that are here. This is how DHCP works. And this is the magic by which we can use IP. When you come in the morning to EPFL, the first thing that your smartphone or your laptop does is connect to a Wi-Fi base station. And depending on where you start your system, you will get an IP address with a subnet that may be different. You can try it. You can come one morning and enter through CE, another morning through BC. You will get different IP addresses because you will be sitting on different LANs when you enter EPFL. There are zillions of other protocols that essentially are doing the same. I will not go through them because they are very simple, except one, this one, which is very frequently seen with IPv6. So IPv6 can use DHCP in exactly the same way as IPv4. There's nothing specific to v4 or v6, except as you can imagine that with IPv6, you don't send a broadcast to the DHCP server or the DHCP relay. Instead, you send a DHCP message to a multicast address that corresponds all the DHCP servers or relays. This is the IPv6 way of doing things here. But there is another way of configuring IP addresses with IPv6 that is automatic and is what we call the test is whether it works in the dentist's office. And the idea is that the dentist usually has a few computers, X-ray machines, imaging machines, wants to connect all that, and does not want to pay a system manager to configure everything, and does not want to learn how to configure everything. So it should be plug and play, even though it's IP. That's the idea. And this was Apple Talk, for example, when Apple introduced its network in the 80s. A bit like IP, it is using addresses. Some of the addresses are names, in fact, with Apple Talk, and it was also totally plug and play. There's no magic. How can you be plug and play? Here is one way to do it. It's called Stateless Address Auto-Configuration, SLAC. And how it works is when a host needs an address, it autonomously gives to itself an address. Without talking to anybody, it says, I will take this address. How do you do that? Well, you take as your host part something that is derived from your MAC address in the simplest case. This is what we will do in the lab. Or you can have configuration that is done by the user. So you give your host part authoritatively without consulting anybody else. If you use your MAC address or something derived from your MAC address, it will be unique unless there is a manufacturer that had a problem somewhere. We have seen also it could be the cryptographically generated address when we've talked of SND, Secure Neighbor Discovery. That's another way. So you give this address to yourself and you don't have to ask anybody because you know the rules for getting such addresses. Then you perform what is called an address duplication test to verify that there's no bug in the system. You send a broadcast. If you would be with IPv4, you would send a broadcast message to anybody asking who has this address. And if somebody answers me, then there is a problem. You should not use this address because if two hosts have the same address, some things are going to crash somewhere. Of course, with IPv6, we don't broadcast, but we send to the solicited node multicast address that corresponds to this host. So I forgot to add that we add, with the host part, we add to it the prefix, that is the predefined prefix for link local addresses. FD something, which means this address is link local. It should never be routed. And if you see this address, it means something only in the LAN at which you see it. Right. So by those two steps, you have, in principle, if there is no collision of MAC address, you have your own IPv6 address, and you can work with IPv6 addresses, at least in the local area network. If you want to work more globally, you need a network prefix. How can you get a network prefix? Well, you can send a broadcast to all routers. In principle, in the normal configuration there is a router on your LAN, which will be your default router. So you can send a broadcast to all machines saying, is somebody a router and what is the prefix of this subnet. Except, of course, with IPv6, we don't send a broadcast. We send a unique a multicast packet to the address, which means all routers that are on link. And if there is a router that is on link, it will respond to you, giving what is the prefix and the network mask. So by doing, this is how the address is derived. I go through that quickly. You'll have time to go through it in the lab, if not done already. So with that, you have an address that is a combination of your MAC address or any other rule you have to make your host part, and what a router has told you is the prefix of this subnet, which makes a lot of sense because the routers must be configured, they must know what are the prefixes that they are handling, but the hosts can easily derive this information. And then, if we go back to the dentist office, what the dentist will need to know is configure which prefix corresponds to which subnet, and all the hosts will do the rest automatically. Now, this is not simple enough. Some people have complained about everything we've said before, about what is called a privacy concern. Right? This is joined with the fact that typically with IPv6 we don't have NATs, which means that our IP addresses are visible globally. Now, some people consider it's a problem. I'm not sure it is really a problem given all the other privacy leaks that exist today. But if you're concerned with not leaking your IP address, then if you're sitting behind a NAT, for example, assume EPFL would have a NAT to connect to the rest of the world. When you would connect from EPFL to the rest of the world, what other people would see is just one of the IP addresses of EPFL that are in the pool of EPFL addresses, but would not know exactly who it is. Right? Same thing for you when you're at home. What other people see is one address allocated by Swisscom or Sunrise or others to you. If you don't like this, you can use what are called temporary address. And the idea is, instead of doing all the smart things we said before, you simply allocate your address as a random number. And this address, you change it once in a while. And in principle, this might cause problem with TCP connections, but we allow with IPv6 to have multiple addresses. So if you have an address that's the one that you're using now and say in 1 hour from now you will choose a new address, then this address becomes deprecated, but can still be used because you may have TCP connections that are open, and depending on the software, if you use many file transfer software, will break if you change the IP address. So you will keep it, but you will not create new TCP connections. So very quickly, this address will be forgotten and another address will be used. So that to the rest of the world, you appear as a collection of random addresses. So if you need this, you can have that stuff here. When we use automatic allocation, SLAC, we get the address and the prefix and the network mask because all that information can be given to a router. Sometimes, depending on the routers are not able to do something else, which is giving the DNS server. So if you need that, you may still need to go to a DHCP server only to get the DNS server name. This has a name, it's called Stateless DHCP. Why do we call this Stateless DHCP? What has state to do in this story? Yes? Exactly. The DHCP server is not storing the mapping IP address, MAC addresses, which normally a DHCP server does. So a DHCP server has state information. It has a table where it must remember which address has been allocated, which not, and to whom it was allocated. Otherwise, it will not be able to give it might cause address collisions. So a DHCP server is in principle stateful. That version of a DHCP server, if the only thing you do is ask, what is the DNS name what is the IP address of the DNS server that I should use in this enterprise, then this is information that of course is a state if you want, but it's a static information. It is not related to the interaction with a given host. Therefore, it is called stateless here. Of course, there are zillions of other variants that I will not go in detail. This is not all very exciting. This is just showing the standard things that we do with address allocation. Here is how things should be if you use IPv6. So how they should be, because we should use IPv6, so we should use what is shown here. If I am at home, Lisa is at home, gets a service from Swisscom, for example, or Simscom in this world here, and uses IPv6. Because IPv6 has such a large address space, what you expect is you get from your provider not one IP address like you get today, but you get a prefix here. So when the router here or the ADSL modem will boot with the Simscom network, it will use one of the protocols that are, when you reboot your ADSL modem, which you have to do in principle every few months, otherwise, because it's a Linux machine, sooner or later it will not be able to survive. It will talk to a router on the provider domain and will use one protocol that could be DHCP. There are variants of DHCP that have other names like PPP, but essentially they are doing the same thing. So it will talk to a DHCP server on the provider network and will get an IPv6 address. For IPv4, that's all that will happen. It would get an IPv4 address. For IPv6, what you would like is not to get an address, but to get what? What would make sense to obtain if you use IPv6? Yes? A prefix, an entire prefix here. So this is what is illustrated in this figure. Lisa has obtained an address for the router, which is the thing here. But you see that Lisa is using the same prefix here. Here the 64 bits are not all the same, but the 56 first bits are all the same. So that means this provider has allocated to Lisa the first 56 bits, so everything up to CC here, that's the prefix allocated to Lisa. So there is a variant of DHCP that will allow you to allocate an entire prefix and not one address. And the benefit is, for Simscom, well, the benefit is you have public addresses, so you don't have that concept of NATs. And for Simscom, there's not much difference compared to IPv4 because all of Lisa's stuff appears as one prefix, which is those 56 bits that are present here. Whether Lisa has one subnet or one host or zillions of subnet is completely irrelevant to Simscom here. Yes?
I have a question. I missed the point about the DHCP server. Why isn't it situated in the local area network? Like when we were talking about the NAT, you said that NAT was integrated in the router in real life. And why don't people integrate the DHCP server in the router? Why is it like somewhere in other places in the web?
So the question is about this DHCP server. So this DHCP server is not used by this PC to get its IP address. It will not be used by this PC. This DHCP server is used by Lisa's edge router, which most of the time we call the ADSL modem. It is used by this modem to get its own IP address. And if it's an IPv6 system that is state-of-the-art, it will also get a prefix. It will know that it has received the prefix here, /56, this prefix. Now this router will allocate to each of its different subnets one of the prefixes and will host a DHCP server for the hosts of Lisa. So when someone will visit Lisa's home and come with a smartphone, the smartphone will speak to the DHCP server that's located here and will get one of these addresses here. You will not speak to the DHCP server of Simscom to get that. You don't want to do that because you don't want to flood Simscom by DHCP requests of all home equipment. So this is how things should be with IPv6. Very often they are not. Very often providers do with IPv6 the same as they did with IPv4, and that defeats the purpose of having IPv6. There is one difference though. If you use this, if you compare to IPv4, with IPv4, we don't do that. It's impossible because the address space is too small. If you want a prefix that would be 24 bits instead of a 32-bit address, it's impossible today. Even getting a new 32-bit address will be difficult. So we do a NAT with IPv4. So the NAT is a drawback because there are applications that may not work so well, etc. But the NAT has an advantage. it hides away from you all the devices out here. If at home you have, like any home, probably 10 to 20 different devices, when you sum up all your own smartphone, iPad, tablet, PC, printer, plus your visitor's equipment, you probably, if you are curious, go to your ADSL modem, you look at your DHCP table, you will see that there's probably 20, 30 addresses that it has given. Those addresses are completely invisible to the rest of the world. So you hide the structure of your network and you hide who is doing what through that. So it is a bit of privacy that is lost when you use IPv6, at the benefit of a simpler network configuration. I will skip those things that we have discussed already. We have seen that with IPv6, it's quite common to allocate link local addresses using Slack. In fact, it's done by default. So if you look at, even if you use DHCP, you will have a link local address. So if you do an IP config in your machine, if IPv6 is on, you should see an FE80 something link local address that is allocated. Similar things were also added to IPv4 with the block 169.254, which is the block of link local addresses. So you can do exactly the same thing as was done with Slack. So when a host boots, it takes one of those addresses. It does an address duplication test by sending a ARP packet to this address. If somebody replies, there is a problem. If nobody replies, it means nobody has this address, or at least nobody that's up now has this address. It's a bit less secure than Slack, because the fact that nobody uses this address does not mean that nobody has it. Perhaps one system has it and it is sleeping, and that's one of the problems with this allocation. But it is sometimes used, or it's used, in fact, in Windows by default. If every address allocation fails, it will use this method here. So let's do a little checkpoint on this here. And the correct answer is D, which is also the majority vote. You need all that stuff, right? So by default, if you use DHCP, you get all that stuff. And when you use Slack, what happens? And you can see the result. C is the correct answer. It was a race between C and A. With IPv6, there is no standard that says what is the host part. You can do whatever you want. And typically, the map from MAC address is what is done very often. That's what we will do in the lab. But it can also be randomly chosen. For example, if you want to have temporary addresses where you don't leak privacy. Voilà, we do a break and resume in 15 minutes.